Okay, the next problem that we will solve is a transportation problem, a very simple transportation problem. Let's see what the problem is. It's also taken from Winston, and this is really a power transmission problem, but the logic is the same whether you're moving electricity or water or boxes of cereal. You are moving things from a point of origin to a point of destination, and there is a cost for moving it. So here you have a generation company, and it has 3 power plants that are called plants 1, 2, and 3, and they are providing electricity to 4 cities, cities 1, 2, 3, and 4. Moving electricity from plant 1 to city 1 has a cost of $8 per unit, and the same for every other combination of plant and city. Now, each plant has a generation capacity. For plant 1, the capacity is 35 units. I'm not going to bother you with the units, a million kilowatt hour, but 35 units. 50 million for plant 2, 40 million for plant 3. This is the maximum that they can provide. And the demand for the cities are 45, 20, 30, and 30 respectively. This is what we need to provide to each city. I think this is one of those problems where the supply matches the demand exactly, which is the case in electricity, by the way, but it's not necessarily the case when you're moving boxes of cereal. So this is what we call a transportation problem. And just so that you have an idea of what the solution looks like, let me show you the solution. This is the solution. We have that plant 1 is supplying all 35 that it can provide. And where is it going? Well, 25 are going to city 3, and 10 are going to city 2. And then so on and so forth. You can see what each plant is giving to each city. And the reason this is the solution is because this delivers our product, in this case energy, at the lowest cost. All right. Now let's see how we would solve this transportation problem, first in SAS and then in AMPLE. Okay, so let's see how we can solve this problem in SAS. We define a set of production entities, which includes plants 1, 2, and 3. We define another set of consumption points, which includes the 4 cities. We specify the cost of moving a unit between the production side and the consumption side. For example, this 8 means that it costs $8 to move 1 unit between plant 1 and city 1. We specify a maximum supply for each production entity. So plant 1 can only produce up to 35, 50, and 40. I'm specifying that number for each producer. I'm also going to specify a demand for each consumer. So consumer 1 is expecting 45, consumer 2, city 2 is expecting 20, and so on. The decision variable is X, which is how many units I'm moving between a producer and a consumer. And this X is going to have the form of an array, of 2-dimensional array. I specify here that it has to be an integer because this model actually came from a problem where I was moving whole things. But for electricity, we could move half a megawatt. We could not move half a box of cereal. So it is not necessary here, but it's good to have it for problems that require the integrality. Our objective function is to minimize the total cost, understood as the sum across producers and consumers of all the things that I move between every production site and consumption site times the cost of moving between those 2 nodes, subject to the constraint that my suppliers cannot provide in sum more than their maximum supply capacity, and subject to the constraint that for each one of my customers, they cannot consume less than, I cannot supply them less than their demand. So their demand has to be satisfied. Then I solve the problem, and I'm going to print the decision variable and the objective function. So I run that, If I scroll down, I see that the total cost of serving these 4 series from these 3 plants, the optimal minimum cost is 1020. And here's the decision variable matrix. I am moving, for example, plant 3 is providing 30 units to city 4. And this is how you solve it in SAS. Let's see now the ample solution to the transportation problem. I have here the model. It defines a set of production entities and consumption entities. Have the same 3 parameters as we saw before in the SAS solution. Has a supply parameter, demand parameter, and a cost parameter. And you can see that supply is for every producer, demand is for every customer, and cost is for every combination of producer and customer. And our decision variable, as before, is a matrix that tells me how many units I'm moving. Same thing as before with the integrality. I do not need to have integrality here for electricity, but I need to have it if I'm moving cars or pallets or something that needs to be whole. My objective function is the same as we saw in the SAS example, and my 2 constraints are the same. This is just a slightly different notation that we use in AMPLE. My data includes the 3 plants, the 4 cities, the supply for the 3 plants, the demand for the 4 cities, and the cost of moving between pairs of cities and plants, all of course given in the notation required by SAS. And my model resets any old model that may be in the memory, calls the new model, calls the new data, specifies Cplex as the solver, solves, and then displays the total cost. And I have added this line here, which is the only new thing here, option display one call. And what this is going to do is that it's going to display this X as a matrix. Let's run this. And here you have it, the same solution as we got with SAS, 1020 for the cost, and here's the solution. City 4 is receiving 30 units from plant 3. You may notice the matrix is transposed as opposed to how we get it in SAS. Those are the peculiarities of each software. But this is how you solve it in AMPLE.